Good evening, friends. We have already discussed in the applied hydraulics about the dimension analysis as module 1, where we have studied about dimensional homogeneity and also about the Buckingham pi theorem and as well as release method, and also we have studied about the model testing in the dimension analysis. In the second module, we have studied the open channel flow, in which we have studied different types of the channel flows like steady, unsteady, uniform, non-uniform, gradually varied flow, rapid varied flow, laminar, transition and turbulent. In the third module, we have studied non-uniform flow, and so today we are going to discuss about the impact of jets. So before going for the impact of jets, let us see how a typical layout of a hydraulic electrical plant will be there. So you can see in the figure a typical gravity dam, in which on the upstream side you have got a reservoir and the water is taken to the downstream side through the big penstock pipes, and there is a nozzle at the down, and this nozzle with a force it will be hitting the blades of the turbines, and this may be flat, inclined, or it may be vertical. So in the layout of a hydraulic plant, you can also see the water level from the head race to the tail race as a gross head, and when there is a loss, when the moving, there we have got a frictional loss. Then when you detect this loss, so then we have got actually net head is equal to gross minus HF, where H is called as the friction loss, is equal to 4 FLV square by 2 GT. And we also know that in the turbines, the hydraulic energy is converted into mechanical energy, which by connecting through a electrical generator, which can be taken as electrical energy. There are different types of turbines like impulse and reaction turbines, and whereas a pump is a typical device or a prime mover where mechanical energy is converted into hydraulic energy. So the main accessories of the hydroelectric plants are a dam which stores water, the penstock which conveys the water, and the turbines which converts the hydraulic energy into mechanical energy, and there is a tail race in which the water after hitting the blades of the turbines will be available in the same form because water is acting as a white coal. So today our main chapter is actually impact of jets. Here we will be studying the force exerted by jet on a plate where the plate is stationary, because the plate may be moving also, but we are studying the force exerted by the jet on a plate and the plate is stationary. There are three different cases. One is plate is vertical to the jet, the second is plate is inclined to the jet, and the third is the plate is curved. In all these three cases, actually we are studying the force exerted by the jet on a plate where the plate is stationary only. So I look at this figure. So we have got a pipe, so which is connected to a nozzle, and the jet is coming here, and actually the plate is vertical here. The plate is shown as vertical. Right? In the figure, V is the velocity of the jet and D is the diameter of the jet, from which you can calculate the cross section area, pi d square by 4, and the component is of the velocity of the jet in the direction of the jet after striking the plate will be 0, because so after striking the plate the jet will be deflected here and its component in the direction of the jet will be 0. So here we will be using the Newton's second law of motion as well as the impulse momentum equation, and the component of velocity in the jet after hitting will be 0. Fx is the rate of change of momentum in the direction of force, that is initial momentum minus final momentum divided by time. So that can be written as mass by time into initial velocity minus final velocity. This can be written as mass per second into velocity of the jet before striking, that is V, and final velocity after striking. So mass per second is rho into A into V, where rho is the density of the fluid, and velocity before striking will be V, and velocity after striking will be 0 in the direction. Hence the equation is Fx is equal to rho V square, where rho is here 1000 kg per meter cube. So this is the force exerted by the jet on a plate which is vertical. So we will take the second case now, the plate which is inclined to the jet here. So here the V is the velocity of the jet in the direction of flow, and theta is this angle, so between the jet and the plate, and A is the area of cross section of the jet. Here also the mass of water moving along the plate is rho into AV as usual. The jet will move over the plate and striking with a velocity v, and Fx is equal to, according to Newton's law of motion and impulse momentum equation, mass into initial velocity before striking minus final velocity after striking. So rho av, and after initial velocity is v sin theta perpendicular to the direction flow, minus after hitting the velocity will be 0, and so it is rho av square into sin theta. And this component can be resolved into, normal component can be resolved into in two ways. One is in the x direction and other is in the y direction. The component of velocity in the x direction of flow is Fn into cos 90 minus theta, that is towards the angle. So that is Fn into sin theta. So Fn is rho av square into sin theta, it is rho av square into sin square theta. Whereas the component in the perpendicular direction of flow is Fn into sin 90 minus theta, that is Fn into cos theta, that is rho v square sin theta into cos theta. So hence when the plate is inclined to the jet, so we have got three things. One is Fn, other is the Fx, other is the Fy. The third case which come across is where the plate is actually curved to have the more efficiency of the water flow. Here also you can see the jet which is coming with a velocity v here, and it is striking a plate, and the plate is stationary but it is a curved plate. So jet striking a fixed curved plate, the jet after striking the plate comes out with the same velocity, and the component of velocity in the direction of the jet is cos theta. So that is in the opposite direction of the jet, we take it as minus v cos theta, and component of velocity perpendicular to the jet is v sin theta. Hence using the Newton's law of second law, so mass per second into v12 minus v2 theta, where v12 is v and v2 is minus v cos theta. So the force in the x direction is rho av into v minus v cos theta. So it is rho a square into 1 plus cos theta. So the component in the x direction. Similarly, component in the y direction is rho av into 0 minus v sin theta, where initially the velocity is 0, where v2y is v sin theta. So it is minus rho v square sin theta. Now we have seen the expressions for the plate which is vertical, the plate which is inclined, and the third plate is curved. In all the cases the plate is stationary. Let us see the two typical examples. Example 1. So here find the force exerted by a jet of water of diameter 75 mm on a stationary plate, normally with a velocity of 20 meter per second. So that means it is hitting the plate normally. The given data will see here the diameter of the jet is given as 75 mm, convert into meter, 0.075 meter, find out the area, so you will get the area. And velocity of the jet also is given 20 meter per second. Here it is a stationary vertical plate. The plate is not moving, right? Hence the equation earlier we have derived, F is equal to rho av square, where rho is 1000 kg per meter cube. Substitute F is equal to rho is 1000 into area is 0.004417 and velocity 20 square. So we will get 1766.8. So this is when the force exerted by the jet on a vertical plate. Now let us take the second example. So it is the plate is inclined to the jet. Find a jet of water of diameter 75 mm moving with a velocity of 25 meter per second, striking a fixed plate in such a way that the angle between the jet and the plate is 60 degree. Find the force exerted by the jet on the plate, 1 in the direction normal to the plate, second in the direction of the jet. So look at the things which are given, the data. D is equal to 75 mm, and you can find the area, and velocity is given as 25 meter per second, and the theta is angle between the jet and the plate is 60 degree. The equation already we have derived. The force exerted by the jet of water in the direction normal to the plate is Fx is equal to rho av square sin theta. So all the things are known here. Rho 1000 A and V is 25 into sin 60. So we'll get 2390.7. The force in the direction of the jet is given by Fx is equal to rho av square sin square theta. So substitute these values. So this is the force 2070.4 is, we'll get the force in the direction of the jet. Thank you.